Hello everyone. What we'd like to do in this video is talk about another way that we can combine functions. We're talking about compositions. Now, what a composition is, or the way I like to think about compositions, is an assembly line of functions. The idea of a composition is super important. You're going to see a lot of it in calculus for those who have to go for that far, but really anything you do in math beyond this point, compositions are all over the place. So there's two main things we want to do in this lecture. One, how do I compute a composition? Two, what's the domain of a composition? Okay, let's first talk about really what a composition is. And I think it's best to lead with an example. So let's say I have two functions. Let's say I have f of x. Let's say I have f of x is equal to, let's say it's the square root of x plus 1. Let's say I have another function, g of x, and that's x squared, let's say, minus 5. Now, when we're computing a composition, what that means is I'm going to take a value, I'm going to plug it into one function, and I'm going to get an output, and I'm going to take that output and I'm going to plug it into a new function. So, for example, let's say that I want to compute, let's say g of f of 4. I'll tell you how to read this here in a second. But what this means is I'm first going to take this 4 value, read it from right to left. I'm first going to take this 4 value, I'm going to plug it into f. I'm going to take that output and I'm going to plug it into g. So as an illustration, g of f of x, what we're going to do is I'm first going to feed in a number into f. So I'm going to plug something into f and we're going to get some sort of output. I always like to think about functions as machines, so this kind of f of, this reads to me like a machine, like this set of parentheses is like what you're plugging the number into, and this equal sign is kind of like it's outputting something. So I'm first going to compute f of 4. F of 4, let's see, what's f of 4? Well, our formula is the square root of 4 plus 1, so it outputs the square root of 5. Now what we're going to do with the square root of 5 is we're now going to plug it into g. So I now have a new machine, call it g, and we're going to feed that, the square root of 5, into g. So I want to evaluate g at the square root of 5, and let's see what we're going to get an output of. Looks like we're going to get the square root of 5 squared minus 5. I wish I had a little bit more board space. Square root of 5. So the square root of 5 squared is 5. I'm going to get 5 minus 5. We're going to get an output of 0. So what we've done here is I've taken 4, I've plugged it into f, and I've taken that output and I've plugged it into g. So g of f of 4 means I'm taking 4, plugging it into f, taking the output, and plugging it into g. So what we've just discovered, I'm going to erase this. So what we've just done here is g of f of 4 we got as 0. Or we could think about it like this. I took 4 and I plugged it into f. We got out the square root of 5. I evaluated g at the square root of 5. And we got root 5 squared minus 5. We got out 5 minus 5. We get out 0. So g of f of 4 is equal to 0. Let's hold on to this. A good question to always ask when you're doing math or when you're coming up with new operations is, does order matter? Is this operation, or the way we're combining function, is it commutative? So let's ask ourselves the question, what if I flip the order of machines? What if I want to compute f of g of 4? So what this means is I'm first going to be feeding 4 into g, and I'm going to take that output and feed it into f. So if we're drawing our machines here, basically I just flipped the order of our machines. I'm first plugging 4 into g. So let's see what we'll get here. So g of 4, okay, wherever I see an x in g of x, I'll replace that with a 4. We're going to get a 4 squared minus 5. And so what are we going to get? We're going to get 9 minus 5. So it looks like we get an output of 4. Okay, so I'm gonna spit out 4, and I'm gonna take the output of 4, and I'm gonna feed that into f. So now I want to compute what is f of 4. Well, wherever I see an x and f of x, I'm going to replace that with a 4. So I'll get the square root of 4 plus 1. I'm going to get out the square root of 5. So this is going to spit out the square root of 5. So what we just did here is we computed g of 4. We took that output, we plugged it into f. We got that g of 4, we got that g of 4 was 4. And I fed 4 into f, and we got an output of root 5. Okay, notice here that g of f of 4 and f of g of 4 are not the same. This will be usually true. The order of composition matters. What we have here is that g of f of 4 is not equal to f of g of 4. In general, g of f of x will not be equal to f of g of 4 of x, doing it in general. Order of composition matters. Now, what's kind of annoying about doing compositions this way is I first have to take a number 4, I gotta plug it into one function, I gotta compute that, and then I gotta take the output and plug it into another function. What I would like to do is just have one machine that does this all for us. So I wanna build this composition. I wanna build this machine. For right now, let's go ahead and build a machine. Build a machine. Let's build the machine g of f of x. I want to build, so what I'm trying to do here is I'm feeding something into f, and then I'm feeding it into g. I'm feeding it into g. So I plug something to f, it then gets fed into g, and that's going to give me another output. But what we would like to do is just have a nice machine that does this all for us. So this is like your cell phone. You plug something into your cell phone and it just does something, but what's going on in between? We're going to try to hide all these pieces. I just want to be able to plug something in and get an output. I don't necessarily care what's going on in the middle. I just want to build this big box that does all the work for me so I don't have to do this step by step. So let's build the composition. Okay, so let's go ahead and build g of f of x. So, okay, what are we going to do? I'm first going to take x and plug it into f. So I need to compute f of x. I need to take that and then plug it into g. So this is what I need to compute. So when I plug a value into x, what does it do to it? It takes that value of x, it adds 1, and it square roots it. So it's going to take a number, x, it's going to add 1 to it, and it's going to square root it. And I'm going to take that result, and that result gets plugged into g. So I just need to evaluate g at the square root of x plus 1. So wherever I see an x in g of x, I'm going to replace that with the square root of x plus 1. So we'll have a square root of x plus 1 squared minus 5. Notice that the square root and the square cancel each other out. So this is going to be x plus 1 minus 5, or we just get 1 minus 5. What do we get? Negative 4. This is just x minus 4. So we've built the machine. G of f of x is the same thing as x minus 4. This is so much easier to work with. This is so much easier to work with. Notice now, if I want to calculate g of f of 4, like we did in the, when we did it step by step, I just get 4 minus 4, I get an output of 0. That was so much easier. I just made this box, I plugged in 4, I didn't see all the gears that happened, but it spat me out 0 much quicker. This is a fast working cell phone. Okay, we need to be a little bit careful though. We need to be a little bit careful. So what we just discovered is that g of f of x was equal to x minus 4. A question we might have, and a good question, is what is the domain? What is the domain of g of f? Now, we have to be careful because you might be tempted, when we end up looking at our result here, we might be tempted, we'll write this in red, you might be tempted, I don't know, here you are, thinking, you might say, hey, I don't know, you have an arrow as a hand. You might say, hey, x minus 4. Hey, there's no square roots here. Hey, there's no variables and denominators. I can make checks on all my lists. You might say, the domain is all real numbers, all x and r. You can plug anything you want into here. No, we have to be careful. This is not true. Sorry. We have to be careful because remember this is a machine, I first had to plug things into F first. And F only accepts certain things. So let me show you what I mean. When I'm finding the domain, a common mistake is to only look at the end result when finding your domain. But we have to remember I first had to run the number through a machine the first machine. So I have to make sure that the first machine accepts all the values. Notice here if I'm drawing our picture, here's F, and here is G. Here is F and here is G. Okay, well, when I feed something into F, notice here that I need x plus 1 to be greater than or equal to 0, or I need x to be greater than or equal to -1. So I can only feed numbers that are bigger than 1 into F. This only accepts x greater than or equal to -1. And now those outputs can be fed through G, and we'll get our outputs. Now, I'll talk about this in a second, but we will be careful about the outputs of F that get plugged into G. But mainly there's two places that you have to check when you're finding the domain of a composition. You need to first check what's going on with the inside function, the first function you're plugging into. You have to think about the domain of your first function, sometimes called the inner function. Remember, this means G of f of x. I need to check the domain of the inner function, and I need to check the domain of the composition. I'll write that down and we'll do some examples. So the domain of this function here, the domain of G of f of x, is going to be all x such that x is greater than or equal to -1. This is the domain. Okay, let's do another example. So I want to write down a key result. The domain of a composition. There's two things we have to check. The first thing that we should check when we do a composition is I want to check the domain of the end result. So what we want to do here is we want to check the domain of the end result. Two, the other thing we have to check is we have to check the domain of the inner function. And the intersection of these two will be the domain of the composition. So there's two things I need to check. I need to check the end result. I need to check out what's the domain of the end result. And I also have to check what was okay for me to initially plug into my machine. Let's do an example. There's two things we have to check. Okay, so let's say we have the function. Let's say it's f of x, which is equal to, let's say this is the square root of 4 minus x squared. And let's say we also have that g of x is equal to the square root of 3 minus x. Let's go ahead and compute f of g of x. Go ahead and pause the video and try to compute f of g of x. Okay, let's do it. So what we have here is what I'm doing is I'm first taking x, I'm plugging it into g, I'm taking the output and then plugging it into f. Okay, so I'm going to first start by replacing g of x with its formula. I'm taking a value x, I'll take 3 minus that value, I'll square root it. Now once I get that output, I'm now feeding it into f. So now wherever I see an x and f of x, I'm going to replace that with the square root of 3 minus x. So here we'll get the square root. We're going to get a 4 minus the square root of 3 minus x quantity squared. Let's see what happens here. Now we're going to get the square root. We're going to get a 4 minus, the square kills the square root. Make sure we keep our parentheses here. We'll get a 3 minus x. This minus sign will distribute. And we're going to get the square root. What are we going to get? 4 minus 3 plus x. Or we're going to get the square root of what? 1 plus x. Or we'll have the square root of x plus 1. Okay, so let's write that result up here. Okay, the square root of x plus 1. So this is our fog machine. Okay, now the question is, what is the domain? Okay, so I'm going to kind of draw a picture here. Okay, we first fed something into G. And then we're feeding that into F. Okay, so the first thing I should check is, well, what could I first been able to plug into G? Well, looking at G, the domain of G, what does it accept? Well, looking here, since it's the square root of 3 minus x, what we need is we need 3 minus x to be greater than or equal to 0. If you solve this, this means that x needs to be less than or equal to 3. So to begin with, I can only plug values into G that were less than or equal to 3. This is me checking the domain of the inner function, So I know that x has to be less than or equal to 3. Okay, so this gets fed in, and then what is it going to output? The end result spits out the square root of x plus 1. So what I did here is I needed to make sure that what I plugged into G was able to accept it. Now when things are being plugged into G, the outputs are being plugged into F. I have to make sure the outputs of G are being able to accept into F. Well, how do I check that the outputs of G are accepted into F? I'm just going to look at the domain of the inner function, the domain of the end result. When I check the domain of the end result, that's making sure that the outputs of G can go into F. So I have to check 2 places. I need x to be less than or equal to 3, but I also need to look at the end result. I also at the same time need x plus 1 to be greater than or equal to 0, or I need x to be greater than or equal to -1. So I need x to be less than or equal to 3, and I need x to be greater than or equal to -1. So here's the domain of the inner function, and here is the domain of the end result. So together, if we want to draw this on a number line, here I have -1. I need x bigger than -1. And we also need all x less than or equal to 3. So this way. So the domain of this composition will be the intersection of these two. So here the domain of f of G is going to be all x such that x has to be between -1 and 3. And that is the domain. I think this is going to be a good place for me to stop the video. In the next video, we're going to do tons more examples. We'll see you then. Take care.